Hi and welcome back. And today we are going to take a look at this aircraft indicator. And this one is a combined processor totalizer. And this unit was manufactured by Smith Industries. On the rear there is a large circular connector. On the front there is a pointer, and there is also a digital indication. There is also a document here. This document is dated 2013. Look at that. We have two CPU boards. The CPU is an ATC31. Thank you very much. And this is the EEPROM, 8 kilobytes. Here we have a part for analog devices, an AD7542. This should be a DAC. We have two low noise op amps here, an analog multiplexer, a MUX08. There is here a CMP01. We have here two power supply supervisory circuits, and here we have another board which is actually the same board. So this is maybe an ARINC 429 interface. Otherwise, effectively, we have exactly the same board. And we have two other boards in the middle here. So this flat flex is connected to this board, which is a connector board. You can see the pass-through capacitors here. It seems that we have the same EEPROM here, the same code, BSP3603, which is the same here. We can see here the first internal board. It is connected to the digital display through this flat flex here. We can see that we have several CD4056. This part is a BCD to 7 segments LCD display. We can see that we have also several CD4094. This is a shift register. The outputs of these shift registers are connected to the BCD to 7 segments display. Therefore, we have an SPI bus here. Here we have a CD4047. This is an unstable, monostable. We have here the power supply. There is here a switched mode power supply regulator. We can see this diode here, an inductor. So therefore the power supply input is here. It is connected to one pin here. We can see here the servo motor. This is maybe a torquer. There is no room for a gear train here. I think that we have a feedback potentiometer. We have here a quad op amp. This is the CD4093. This is a quad NAND gate with Schmitt trigger inputs. And we have several logic ICs. I guess that one of these transistors, or maybe both of them, are used for the torquer. I found on internet a document regarding this instrument. So we can see inside we have these two identical CPU boards, which are the left processor and the right processor here. This unit is connected to two tank probes, one for the right tank and the second one for the left tank. The pointer here indicates the sum of these two quantities, and inside there is also an ADC which permits the measurement of these two voltages, and the sum is also displayed on this LCD here. You can see that this unit is expected to be connected to the fueling control panel. It is something equivalent to the fueling control panel I have described a few weeks ago concerning the Fokker 100. This instrument is used for the Fokker 50 and 60. The Fokker 100 has also a central tank, but I think it is possible to connect this unit to the fuel panel of the Fokker 100. We have here the block diagram of this unit. The tank probes are here. There is one probe for the left tank and another one for the right tank. For each channel there is a sine generator. The voltage is 22 volts RMS, frequency 30 kHz. Depending on the quantity, there is a change of the capacitance here. The current is proportional to the value of this capacitance. We can see that on this instrument we have two TIA, transimpedance amplifiers. It permits the conversion of a DC current into a DC voltage as the output here. So therefore we need a DC current. I guess that we have a circuit close to this one with two diodes in order to have a DC current here. On this line we have a single wave rectifying, and we have exactly the same circuit for the second channel. These two voltages are converted into two currents flowing through these resistors there, and we have here another TIA. So therefore at the output we have a negative voltage, which is an image of the sum of these two currents, that is to say the sum of the tank quantities here. This output is fed to this inverting amplifier. This permits to have a positive voltage on that point, which is applied to the servo control system here, and this permits to set the pointer. Therefore, the pointer indicates the sum of the quantity inside these two tanks here. Also, these two outputs are fed to an ADC. This permits a digital acquisition of the quantities. This signal is also fed to the ADC. I have here one example of a tank probe. It was not used in a Fokker aircraft, but in another aircraft. The length is approximately 1 meter. We can see we have inside two concentric tubes, and the capacitance of the system depends on the quantity of fuel inside. I have connected two variable capacitors here for the simulation of the two fuel probes. The capacitance can be adjusted from 50 picofarads to 600 picofarads approximately. And you can see that this thing works. So we have the analog indication and the digital one here. You can see that we have the sum of these two values. You can see that there is a large time constant here. I think that we are above the limit. On the board, there is an RS422 interface here. As the output, we have a signal which is compatible with the tank quantity panel, this one here. And the timing of the signals is identical to what I have used for the prototype. There is a period here of 80 microseconds and 60 or 20 microseconds for a high-level bit and a low-level bit. Incredible. Let's turn on the power supply of the panel. And you can see that this thing works perfectly. I can adjust the right quantity here and the left quantity. Currently there is a capacitance of 400 picofarads approximately for each variable capacitors. I think it should be possible also to adjust this required quantity here. For that I need to connect this commutator to this indicator, but I have to do some code reverse engineering first. This video took me approximately 1 week. That's all for today. Thank you for watching and see you next time for another video. Bye bye. We can see here the schematic diagram of the 30 kHz oscillator used for the tank probe. The main oscillator is here, so this is an auto-oscillant circuit. The output amplitude here depends on the power supply of this oscillator. The power stage uses this LM140, which is actually a 5 volts regulator. So therefore at the output there is a voltage corresponding to the ground voltage here plus 5 volts. This is the power stage of a poor man's. The output voltage is applied to this capacitor, so therefore there is an AC current. The AC current depends on the value of this capacitor, so this capacitor should be very stable. This AC current is converted into a negative DC current here using these two diodes. So we can see that we have a transimpedance amplifier. At the output there is a positive voltage, and this positive voltage is fed to this integrator, and there is a reference voltage. This DC voltage permits to set the output amplitude, and the output of this integrator permits to modify the output voltage through this power stage. We can see that the current depends on the voltage drop of this diode. When the temperature increases, the voltage drop increases, so therefore there is an increase of the output voltage because we need more AC voltage here to give the same average current flowing here. Therefore there is a temperature compensation which uses this diode. When the temperature increases, we have the same increase of the voltage drop across this diode, and this permits to reduce this voltage, therefore there is a decrease of amplitude. So if we take a look on the routing, we can see that these two diodes are close together in order to have a minimum temperature gradient between these two diodes. It is possible to calculate the output voltage here. So first, because of this regulation, we have here a voltage of 5 volts DC. We can calculate the average current flowing through these feedback resistors here. So this is 5 volts divided by these two resistors in series. So there is a total of 27.5 kilo ohms approximately. We can calculate the peak current flowing through this capacitor, which is identical to the peak voltage minus a voltage drop here, I called VD, divided by the impedance of the capacitor, that is to say, multiplied by the capacitance, multiplied by omega, 2 pi multiplied by the frequency. And this is identical to the average current multiplied by pi, because when you have a single wave rectifying, the average current is the maximum current divided by pi. And after calculation with actual values, we find a value of 21.94 volts RMS. I have measured the voltage of 22 volts RMS. So we have here the schematic of the servo control of the pointer here. There are different blocks. The servo control itself is here. It permits to drive the pointer according to the DC voltage present on that point. So there is a comparison between the input voltage here and the voltage which is given by the feedback potentiometer. This voltage is strongly amplified. We have a DC gain of 1000 approximately. This circuit permits to the pointer to return to the home position when the power supply is off. This is a torque motor, but without spring. That is to say that the pointer is free. So when the power supply is turned off, we need to apply a positive voltage in order that the pointer returns to the home position. So this is the goal of that circuit. We have here a reservoir capacitor. These capacitors are charged with a voltage close to VDD using these two diodes. And you can see also that we have here a PNP transistor connected to VDD. When VDD falls after power off, this transistor turns on because this voltage is still present because of this reservoir capacitor, and the capacitors are discharged to the torquer here in order to set the pointer to the home position. The input of the servo control is here. This input here is connected to this analog switch. This permits to select between the normal mode. This is the TIA, which permits to have the sum of two inputs currents corresponds to the right and the left tank quantities at this output, and there is a negative voltage. This voltage is fed to this inverting amplifier, and the output here is fed to the servo control. Otherwise, there is a test mode. In test mode, the switch here is on the other position, and there is a sequencer circuit on the bottom of this page which permits to set a voltage corresponding to the maximum indication or to the minimum indication using this accurate voltage divider here. The sequencer is here. There is a 555 which gives a clock frequency which is fed to this binary counter. The test is activated by connecting this line momentarily to the ground. There is a flip-flop here. And we have something like that. The test mode is activated a few seconds, so we can see that we have two cycles in between here. One cycle permits to set the pointer to the minimum position, and just after to the maximum position here. Now here we have the ADC of that system. It is a successive approximation ADC. The main part is this DAC here. At the output, we have a negative voltage. On that point, we have the sum with different coefficients of these two voltages, the input voltage and the variable voltage here, which is negative, which is set by the DAC. And this voltage is compared to 0 using this comparator, and the output is fed to the microcontroller. The microcontroller will change the content of the DAC in order to have here a voltage which is close to 0. It uses the successive approximation algorithm. At the input, we have this multiplexer. It permits the measurement of different voltages. We can see here the code for the successive approximation ADC. The registers R4 and R5 contain the mask. It is initialized for the MSB of 12 bits here. The result is initialized at 0. The result is ORed with the mask. After that, the result is fed to the DAC. This is this code here. There is a delay for the stabilization of the hardware. And after that, there is a test of the output of the comparator. If the output of the DAC is higher than the voltage to be measured, the mask is removed from the result. After that, the mask is divided by 2, and this process repeats 12 times.